Let's do part 1 of lab 21, which is our first fully digital lab. The previous lab about FETs was kind of a segue from analog into digital. So we have wired up, so I wired it up here and I drew it on the board. We have a Cmos Nand gate. So this is it's pretty, you'll see a lot of these. It's pretty typical format. I mean, kind of old-fashioned at this point. If you're making a circuit board now, you use surface mount parts instead of parts that poke through the board, but this is handy for breadboarding. 14-pin DIP. DIP is dual inline package, so I guess we've been using DIPs since our op-amp days. So these 14-pin packages, almost always they have ground as pin 7 and VCC as pin 14. And you do want to be sure that the first thing you do when you push this into the breadboard is connect ground to pin 7 and VCC to pin 14 so that you don't forget, because Cmos logic has a funny way of working intermittently if you have the logic inputs connected but no power. So sometimes it will work intermittently if you have no power on account of there are protection diodes at the inputs to protect the inputs from electrostatic discharge. And sometimes these can intermittent or kind of inadvertently or in confusing ways create power connections, but the power connections are there or not there depending on the logic state of the input. So it's an extremely confusing thing to debug. So remember, connect VCC and ground first. So we have here our Nand gate. So you say, oh, how do we connect that? I just used the first Nand gate in the package. So here is pin 1, and here is pin 2, and here is pin 3. And then this 100 ohm resistor is just to limit the current that goes through the LED. So this is a red LED, so the voltage drop when it's on is about 2 volts. So if that's 2 volts, and this is 5 volts, so for Cmos logic works in a way that's pretty easy to understand. So if your power is 5 volts, then logic 1 is 5 volts, or within a couple tenths of a volt of 5 volts. And the logic 0 is 0 volts. So that's pretty easy to follow. There are other logic families, older ones, that whose high and low levels are quite different. But so Cmos is actually quite nice this way. And then where it transitions on an input from being 0 to 1 is pretty close to 2.5 volts. About halfway between ground and VCC. We'll see. Actually, a spec sheet specifies a minimum and maximum, but it's typically pretty close to 2.5 volts. So I guess presumably that corresponds to V threshold for the particular MOSFETs that are used in the circuit. Okay. Right. So if this is 2 volts, then if this is 5 volts for logic 1, then the difference is 3 volts. 3 volts divided by 100 ohms is like 30 milliamps. Okay, so we'll run like 30 milliamps through this LED. That should light up the LED pretty brightly. Actually, you can see that. The LED here is lit up pretty brightly. What's happening on the input? So if you were just going to wire things up by hand, you could connect this by hand to plus 5 volts to make it a logic 1. And you could connect it by hand to ground to make it a logic 0. So why do we have resistors? Well, these switches, so there are some switches, I can never remember what's called, I think this is called double throw. There are some switches that that look like this schematically. So you could say, okay, here is my logic pin. And then this is like plus 5 volts, and this is ground. And so then you can have the switch kind of go back and forth. So depending on which way you push the switch, it either makes a definite connection to plus 5 or a definite connection to ground. So that's kind of a handy format for a switch. Unfortunately, well, I don't know. It just turns out that the most simple push-button switches to get aren't like that. Instead, they have two electrodes here. So here are my two electrodes. And it actually looks just like the symbol. So, okay, and then here I have this is the little button I push. And here's a spring that holds it up. And so this goes to one place, this goes to another place. Here, I'll call this A and B. So if I don't push the button, then there's an infinite resistance between A and B. So A and B are not connected to each other at all. I push the button down, and now there's zero resistance between A and B. A and B are short-circuited to each other. So it's either an open circuit or a short circuit. So that's the most typical kind of switch you'll find. So that means somehow you have to wire that up in such a way that you can connect the input of your logic pin either to +5 or to ground. So here it is. When I push the button, it's connected to +5. This one, when I push the button, it's connected to +5. So why don't I just wire this straight down to ground? Well, if I wire this straight down to ground, that's perfectly fine when I'm not pushing the button. So when I'm not pushing the button, then the input is ground. Good. But now what happens when I push the button? Now when I push the button, I have a fight between an excellent +5 volts, like a strong 5 volts and a strong ground. So if you have a fight between a strong 5 volts and a strong ground, who wins? Who knows? I mean, it depends on what the resistance to ground is here, and it depends on what the source resistance or output resistance is of this power supply. And if this is a really good connection to ground, then you might cause this power supply to blow a fuse or to trip itself off on an overload condition, or you might run a lot of current through your wire. So you don't really want to fight between two strong power supplies, or between a strong voltage source and a good ground. So what you can do instead is you make this a poor ground. I mean, it's a kind of medium quality ground. So if this switch is open, this is an infinite resistance, and here's a finite resistance. So a finite resistance wins over an infinite resistance. So if the switch is open, then each one of these is connected to ground. If the switch is closed, well, this is like zero resistance. So zero resistance wins over a finite resistance. You see, so a finite resistance beats an infinite resistance, and zero resistance beats a finite resistance. So that's kind of neat. I mean, it's not really infinity or zero. This is more like, when you connect the switch here, it probably is just a few ohms to +5. So a few ohms, if you have two paths, one is 100 ohms and one is a few ohms, you know just from drawing a voltage divider that the voltage will be very close to the few ohms path. And then if you have two paths and one of them is 100 ohms and one of them is, I don't know, hundreds of millions of ohms, then the 100 ohm path will win. So that's the idea. The idea is you have this medium, kind of moderate resistance. So if it's a competition between this and an open circuit, this wins. If it's a competition between this and a short circuit to a power supply, the short circuit to the power supply wins. That's a neat trick. Okay, let's try this thing out. Let me show you how I have the setup here. So actually the setup in waveforms is very easy here. So the only thing I care about is supplies, and the only supply that I use is VCC, and my VCC is set to 5 volts. So everything else I have off, just to make sure I don't accidentally connect something to +9 volts. I don't think it would do that much harm. It might blow out the LED. I don't think it would do that much. But anyway, so we're using only +5 volts and ground. Okay, so then my convention is ground is down here, this blue stripe on the bottom, and then VCC, the fixed 5 volts or 3.3 volts, it's always been 5 volts so far, is this blue stripe up here, And then I always reserve this red stripe and this red stripe for +9 and -9. So this push button, its left side goes up to +5, and then its right side goes over to pin 1 on this 14-pin dip. This push button, same story. Its left side goes up to +9. 5. Oh, +5, +5. I hope I didn't say +9. Its left side goes up to +5. Its right side goes over to pin 2 of this 14-pin Cmos, 14-pin dip. And then here's 100 ohms to ground from pin 1. Here's 100 ohms to ground from pin 2. Now at pin 3, I have 100 ohms going over to this column. And then from that same column, I have a red LED going to ground. And the long lead of the LED is here, and the short lead of the LED is going to ground. So that when this is +5, when this is +5, the LED lights up. Now you can see I'm not pushing anything, and the LED is lit up. If I push only the left button, the LED is still lit up. If I push only the right button, the LED is still lit up. But if I push both buttons at once, then the LED goes off. Okay, so it seems like the only way I can get the LED to go off is by pushing both buttons at once. And I guess we can work out a truth table to see that. One more thing I want to do before we do that is I want to talk about the push buttons shape. So my box of parts has two different kinds of push buttons. I'll call them the good ones and the less good ones. So the good ones look like this. I'm holding it in a pair of needle nose pliers. So it has just two leads, and they're nice and straight, and they're well spaced out. So this is very easy to use on a breadboard. You make sure the two sides go into two different columns, and then you just make your connections in the obvious way. These are like a new purchase. So what we have used in the past are these much less nice buttons. I'll call these the less nice kind. These have not 2 legs, but 4 legs. You might wonder, why does a device that has only 2 terminals need 4 legs? Maybe it's mechanical. And then you have to wonder, well, which ones are connected to which? And I find myself, anytime I use these, I have to use the ohm meter to beep out and see what's connected to what. Because I think these two are connected to each other, and these two are connected to each other, something like that. So I think like these two are the same, and these two are the same. So every time you use it, you have to make sure you understand which things are internally shorted together, and then you want to make sure that the things that are not internally shorted together go into separate columns. I guess another way you can use this style is you can put it across the little bridge there, like that. Anyway, so I don't really like these buttons. I like these much better. So if you have both kinds, I would recommend using the 2-pin kind. If you have only the not-so-good kind, do reach out to us if you have any trouble figuring out how to use them. Okay, now, truth table. So this is something we do with Boolean Logic. So you say, here, let's call the two inputs A and B. Let's call this A, we'll call this B, and we'll call this out. So we make a little truth table, and the thing about binary is there are only 2 possibilities. So it's easy to enumerate all possible states. So now we could say 0 and 1, or we could say low and high, or we could say true and false. Right, so we often say 0, or low, or false. And then we often say 1, or high, or true. And then sometimes we're explicit about voltages, like we might say ground, or we might say +5 volts, or we might say VCC, So anyway, I'm going to say true and false. So let's say false, false, then this actually, you know, I'm going to say low and high. I'm going to say low and high because we're looking at voltages, and it's unambiguous which voltage is lower than the other. So let me say, and this, by the way, this is A and B. It's the opposite of. Okay, so it's the opposite of A and B. All right. So I'm going to say low, 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 high, high, low, high, high. All right. Low and low is false, and the opposite of false is true. So this will be high. Low and high is false, so the opposite is high. Low and high is, yeah, so false, false, its and is false. I guess maybe I should do it with true and false. Okay, anyway, high, 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 low. Okay, maybe it is easier to understand if I say false here. I can say false, false, true, false, false. Oh, that's not false, that's true. Could be time for more coffee. Okay, false, true, 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 false, true, 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 false. Okay. It's kind of confusing because it should be, it's like the opposite of and, you know, so with and, you know, you have low, 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 high, so it's just the opposite of and. All right, so you say, okay, see, there's something here and there's something here, so you have to have both. So it's like that except it's the opposite, so it's high, 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 low, whereas the ordinary and would be low, 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 high. Okay. So that's what we saw. We saw if they're both low, the output is high. If one is low or the other is low, the output is high. If they're both high, the output is low. Okay. So that's that. That's part one of, oh, that's part 1.1. Aha, that's part 1.1 of lab 21. So I'm going to move on to do the rest of part one. I was wondering how that could have taken 45 minutes. Okay, so I guess we will move on, and I'm going to pause, and then I will wire up part 1.2 as part of the same video. Okay, what we are doing in part 1.2 is we are eliminating this switch and replacing it with a direct connection to +5 volts. And it doesn't make any difference whether we leave this resistor here or not, but let's remove it. Okay, so this connection is still the way it was, but this is now a direct connection to +5 volts. So then you say, which of these combinations are still relevant? And so this input is always high. So input A is always high. So these are not relevant, but these are relevant. Okay, so now basically, see, if this is low, then this is high, and if this is high, then this is low. So the output should always just be the opposite of my one remaining push button input. Let's see if that's true. Let's see if that works out. So when I'm not pushing the push button, then input B is low, and the output is high, as seen by the fact that the LED is on. And if I push the button, now input B is high, and the signal going to the LED is low. See, now input B is low, and the signal going to the LED is high. Now, actually, it occurs to me, I could, maybe I'll do that. So I'm going to set up the scope so you can watch it on the scope too. Okay, this was actually more interesting than I expected because so I have scope channel 1 in yellow is looking at input pin B here. That's pin 2 on the 14-pin DIP. And then I have scope channel 2, which is blue or cyan, is looking at the output, which is pin 3 of this 14-pin DIP. And the first thing I noticed, which was surprised me, is that the output is just a little above 4 volts instead of 5 volts. And I thought, gee, it contradicts what I told you earlier. But I think it's because we're putting a significant amount of current into this LED, right? It's about 30 milliamps. So if I just pull this LED out, see, now we're at 5 volts. So the true output really is 5 volts. But if you load it by making it supply a large current, then it reduces. I guess that tells you, well, I guess you could infer something about its Thevenin resistance by noticing that if it supplies 30 milliamps, then instead of 5 volts, it's 4 volts. Let's see. Well, okay. Anyway. Then, if I push the button, oh, you also see the input is 0. So then, if I push the button, the input is 5 volts, and the output is 0. Oh, it's you kind of see this color is reversed. So yeah, push the button, input is high, output is low. Release the button, input is low, output is high. All right. And then again, just for the scale, this is 0 volts, 2 volts, 4 volts. So 5 volts would be, and this is 6 volts. So 5 volts is halfway to that next tick. So that really is 5 volts, and the output is 0. And now the input is 0 and the output is probably 4.2 volts, 4.1, 4.2. Okay, so that was part 1.2. Okay, now what we've done is we've eliminated the switch that was providing the input to input B, and we just replaced it with a floating piece of wire. So you can see that. Well, let's see if you can see that. Here, let me zoom out so you can see that. Okay, I think you can see that now. So here is the wire going from pin 2 to nowhere. Okay, it's a wire to nowhere. And then I have a piece of red wire hanging out of the +5 here, and I have a piece of black wire hanging out of ground here. And so you know this thing is set up as an inverter. So if I connect, because I have the input A is already going to +5. So if I hold this to ground, then it stays in its, the LED stays in its on state. If I hold this to +5, the LED will go off because the output just does the opposite of what the input is doing in this configuration. So what's sort of neat is I can, if I hold this wire with my left hand and I grab ground with my right hand, the LED stays on. I guess that's not too remarkable. Then if I hold this LED with my oh gosh, if I hold this LED, if I hold this wire, if I hold the wire with my right hand and, and I grab the +5 with my left hand, then the LED goes out. Now actually, unlike, see there it even stays out for a while. Yeah. I think it will eventually come back on, but so this is sort of the float. Yeah, now it's back on. So this is the sort of floating Cmos input phenomenon. There you go. So you can see that it's on. And I guess if I grab these with 2 different fingers, it goes off, stays off for a while. So I think The slightly different behavior from what you saw with the straight MOSFET in the previous lab is, I think, the behavior of the protection diodes. I think a little bit of charge can be left on the gate of one of these inputs, but I think it's sort of slowly drained off by the protection diodes. Okay, anyway, I think it's kind of neat though that I can touch, +5 and the input pin with fingers from 2 different hands, and I can change the state of the output in a way that, and it stays that way at least for a while until the charge very slowly drains off. Okay, so yeah, that's kind of like what we saw with the light bulb and the Cmos input in the previous lab. Okay, now for part 1.4, we have replaced this, well, now input B, pin 2 of this 14-pin dip. Instead of being driven by a wire that I'm touching with my hand, or being driven by a push-button switch, instead it's being driven by the arbitrary waveform generator. So I have set up AWG channel 1 to, this is a triangle wave. And it's a triangle wave that goes back and forth between +5 volts and 0 volts. And right now it's going back and forth at 1 hertz. So let me show you. Oh, and then I guess you can kind of see because the output LED is blinking at 1 hertz. That sort of makes sense. Okay, then let's see how I set that up. So power supplies, as usual, only VCC, well, for this lab, only VCC. Wave gen, I'm using a single channel of the AWG, 1 hertz triangle, amplitude 2.5 volts, offset 2.5 volts. So it goes back and forth between 0 volts at the bottom and +5 volts at the top. And then I go over to scope. I'm using 2 scope channels. So I have channel 1 looking at what I'm sending in, and I have channel 2 looking at what's coming out. So basically, scope channel 1 is looking at the AWG output, which is going into pin 2 here. And scope channel 2 is looking at pin 3, and then the LED and the resistor together in series are also looking at pin 3. And then if I tell the scope, well, actually, so if you look at the frozen picture here, you can see that when the input is high, the output is low. When the input is low, the output is high. Okay. And if we say go, actually, now I have this in shift mode. Most oscilloscopes refer to this as roll mode, but this scope calls it shift mode. And this is actually useful for looking at things that are slow, kind of low frequency. So if you have a time scale that's kind of like on the order of 1 second per division, or a tenth of a second or a few seconds, then this is kind of like it's like a chart recorder type display. It sort of looks like, it actually looks a lot like the electrocardiogram display you might see in a hospital, or it's also kind of reminiscent of the old-fashioned paper tape chart recorders that you might have seen in like really old movies about seismographs or electrocardiograms. Anyway, you can see, actually let's stop it now, and you can see, okay, so when the input is below about 2.5 volts, the output is high. When the input is above about 2.5 volts, the output is low. And I guess we can go back to kind of regular triggering. And then maybe we can look more closely at what happens near the trigger. So let's look pretty close to, let's see. Let's look pretty close to where it triggers. And you can see, well, actually, this is kind of interesting. It's kind of taking its time. So, but you can see that something happens when the input crosses, looks like about 2.4 volts. And then over here, something happens when the input crosses, looks like about 2. Wait. Yeah, 2.4 volts, and this is like 1.8 volts. So it seems like, yeah. So it seems like there's this kind of slow transition range, but it seems as if so the input is considered above threshold if it's above, looks like about 2.4 volts. And it looks like if it's below about 1.8 volts, it's considered below threshold. And then the question is what happens in that intermediate region. And then I guess another thing is we might want to know whether what happens in that intermediate region depends on what's plugged in. So if I get rid of this LED so it's not very heavily loaded. Oh, that's interesting. Okay, so it seems like, okay, it seems like that is kind of an intermediate. So there's usually a region very close to threshold where it's not sure whether its output should be, well, whether the input should be considered high or low. So the way you infer what it thinks about its input is you see what it does to its output. So there's this sort of like kind of indeterminate region very close to transition. And it's kind of interesting to see where that region is. It's like where does it decide the input has gone from being in the high state to the low state, or vice versa? Let me change the trigger to falling. Yeah, okay, that's interesting. We see a similar phenomenon. Here, let's go see what we wrote up in the lab instructions for what we're supposed to look at next. Well, first, it suggested 10 hertz. I wanted to use 1 hertz at first so you can really very obviously see it blink. Let's see what it looks like at 10 hertz. So if we go to wave gen, change this 1 hertz to 10 hertz. Okay, I guess, so with my eye, I can definitely see it blinking at in a very periodic way. When I look at the computer monitor, it looks like there's some kind of sampling problem. So it seems to blink intermittently, but if you look at it in real life, it really blinks with a perfectly regular pattern. Okay, I think the next thing we're supposed to do is go to a kilohertz. Okay, let's go to a kilohertz here. So instead of 10 hertz, we'll go to 1 kilohertz, 1,000 hertz, and then we'll look at Mr. Scope here, and we want to zoom in to, I don't know, something like a millisecond per division. Okay, so again, you see input high, output low, and vice versa. So now let's zoom in even more closely. And yeah, you can see it looks like when the input is, well, that's, okay, so now it seems like that's like 2.3 volts to 2.7 volts is where the transition seems to occur. Oh, that's in one direction. Let me do it in the other direction, right? That was the falling trigger. Rising trigger, this seems like 2.4 volts to, okay, right, 1.8 volts. So I think we're seeing the same transition points at a kilohertz in voltage. I think we're seeing the same voltage transition points as we were seeing at the slower speed. Yeah, it's interesting to kind of observe which of these things might be voltage effects and which ones might be like somehow time related. It seems like it switched it started to switch and finished switching at the same two voltages when we were going at 1 hertz versus when we were going at a kilohertz. So I think that's kind of interesting. And it also seems as if the transition on the way up is slightly different from the transition on the way down. I don't know if I have a good explanation for that. Okay, so the one last thing we're supposed to do is replace the triangle wave with a square wave, and then see if we can see the delay from the change in input to the change in output. So if you look on this scale of, like, here's 100 microseconds per division, it seems like on the scale of 10 microseconds, it's instantaneous. So let's zoom in a little more on the time axis. And it still looks instantaneous, so let's zoom in a little more. And it looks almost instantaneous, and let's zoom in a little more. Okay, so now it's starting. Now actually here, I think that we're running into the limitations of our home oscilloscope, because if you use the real laboratory oscilloscope, I think you can pretty clearly see a difference. So it's pretty hard for us to see. Actually, I remember this from last year. Yeah, it's pretty hard for us to see a difference here. With this EE board. Let me just also pull this out. So I pulled the LED out in case that big current is slowing things down. So it seems like it's pretty hard for us to tell. That's falling. Let's go to rising. Yeah. Okay. Well, it seems like maybe we can put a bound on this. This particular exercise might be better in Circuit Lab than in the EE board. So I think with a faster oscilloscope, I know with the stuff we have in our classroom, we can see this pretty clearly. So I guess the data sheet for this logic family, the 74HC logic family. Oh, by the way, I noticed that on my little parts kit, it's written 74HCT00, but then I looked at the chip, and the and the chip says 74HC00. So it really is 74HC00. It's not 74HCT00. So I remember when I first learned electronics and the digital part of the course, one thing that I thought was incredibly annoying and tedious and difficult to remember was the stuff about different logic families. So it turns out you can use MOSFETs to make logic gates, or you can use bipolar transistors to make logic gates. And when you do use bipolar transistors, there's several different ways you can wire them up. And when you use MOSFETs, you can build them in such a way that the threshold is right in the middle, like at 2.5 volts, or you can make them so that the threshold is different. And so an old-fashioned logic family, which was very widely used until, I don't know, 25 years ago, was called TTL, transistor logic, which was made out of bipolar junction transistors. And it had logic thresholds that were much lower than the 2.5 volts you typically see with this Cmos outputs. So HCT means that the gates are made from Cmos, but the input thresholds are TTL thresholds, which I think means that anything above about 1 volt is considered a logic 1, and anything I think to be a logic 0 has to be below 1 volt, maybe even below like 0.8 of a volt. You have to check that number to be sure. I don't remember it anymore, but I do remember the TTL low to high threshold is a lot lower than you would expect from. It's not anywhere near the middle of the 0 to 5 volt range. It's much closer to about 1 volt. And actually, for noise immunity, In other words, you want like a little noise wiggle on your input, not to change the answer. So to get maximum noise immunity, you really want the threshold to be sharp and to be in the middle of the range. And a normal Cmos logic gate does that. But so HC is ordinary high-speed Cmos. HCT is high-speed Cmos with TTL thresholds. Normally you don't want this unless you're interfacing to old-fashioned TTL logic. So I actually don't think we have any of this stuff. So I think it really is HC, not HCT. At one point, we might have had a mixture of CMOS and TTL stuff, so it might have made sense to buy HCT, but I'm pretty sure these days we just buy CMOS stuff. So it really is HC. It's not HCT, and it's not TTL. Anyway, okay. So the 74HC00 datasheet specifies a maximum propagation delay less than 23 nanoseconds. Typical value around 9 nanoseconds. So that means from the time the input changes to the time the output should change should typically be about 9 nanoseconds, and it should always be less than 23 nanoseconds. And I think our scope just is not fast enough to see that, because here we have 20 nanoseconds per division, and you can see that it looks like the interesting stuff is happening on kind of that time scale, but you really can't see what happens before what at this level of precision. So this is something we will have to, maybe we should make a video of this next year when we're actually in our ordinary classroom. You know, I actually do have a real oscilloscope over on the end of my basement, but the question is, do I really want to set it up for this? Maybe I will. Okay, so we are now looking at the screen of my real oscilloscope. Even this oscilloscope is not a real oscilloscope by the standards of what we use in our lab, but it's pretty decent. So right now our time scale is 200 microseconds per division. And then our vertical scale is 1 volt per division. And there's a little offset between, oh, I think I might be able to get the intensity such that you can focus a little better. Let me see. Let's see. Okay. Seems like the focus is kind of coming and going. Oh, that's a little better. Huh. Oh, okay. That's not too bad. And I was going to move the vertical position so that you can see a little more clearly. Okay, so channels 1 and 2 are on the same scale now. Yeah, the camera looking at the scope is not ideal, I guess, but well, still, I think we'll make this work somehow. Somehow we'll make this work. I wonder if more background light would make this work better. I don't know if it's better or worse. That might be worse. Okay, anyway, what you can sort of see, maybe you can see, is there is an abrupt transition from, okay, so here is high, low, and then that's channel 2. Channel 1, high, low, and oh, okay, then let's zoom in on the time axis. So that was 200 microseconds per division. There's 100 microseconds, 50 microseconds, 20 microseconds, 10 microseconds, 5 microseconds, 2 microseconds, 1 microsecond. Oh, now we're starting to see something happen. 500 nanoseconds, 200 nanoseconds, 100 nanoseconds, 50 nanoseconds, 20 nanoseconds. And again, this scope is not nearly as good as when we have in our lab. This is, okay, 10 nanoseconds per division. So that's pretty good. 5 nanoseconds per division. That's maybe even a little better. So I think you can see that the input transition happens somewhere around here, and the output transition happens somewhere around here, and it's 5 nanoseconds per division. So I think you can see that the output transition happens about 10 nanoseconds after the input transition. This is going from low to high. And then let's change the trigger so we trigger on the other side. So here is from high to low. Okay, and I think you can see the high to low transition on the input seems to happen probably somewhere around here. And then you can see the transition on the output happens a couple boxes later. So I would argue, yeah, I would argue it's about 10 nanoseconds from the change in the input to the change in the output. And maybe it's a little more obvious if you look at it this way. Yeah, so this is 50 nanoseconds per division. And you can see the input is changing around here, and the output is changing around here, which is probably around 1 or 2/5 of a division later, which is like 10 or 20 nanoseconds later. So I think that makes sense. Okay, so I don't know, I guess that was kind of worth doing, setting up the other oscilloscope. I'm annoyed that I think it's hard for me to set up this camera to be compatible with the current light level, but at least you can see that with a little bit better time precision on the oscilloscope, we can see that there's sort of a 10 to 20 nanosecond delay from the change of the input to the change of the output. All right, and I think that was worth seeing. It's definitely something you can see with our equipment in the real lab. So I believe that is now everything for part 1. So we'll go on to part 2 in the next video.